Thank you for being here today at Bash. If you can invite everyone to take your seats. There are extra stools by the side. There are not enough seats around. And just make yourselves comfortable. So thank you once again. Welcome to Bash. This is our other location belonging to SGInnovate. If you don't know what Bash stands for, Bash actually stands for Building Amazing Startups here. So we're trying to build as many amazing deep tech startups in Singapore and at Bash and at with SGInnovate as much as we can. And today we're very happy to have another event, another quantum event with the Center for Quantum Technologies. And today we have a very special guest, Chris, who will be taking us through his presentation over here. So without further ado, I'll invite Chris on stage over here. Thank you, everyone.
So now I can't speak loud. Okay, well, thank you for the invitation. And just sort of scanning the audience, there's some familiar faces, experts in the field, but also it looks like there's a lot of industrially minded young people and people of all ages that are maybe not a lot of quantum physics trained folks. How many of you have ever had a course in quantum physics? Okay, all right, that's good. We can ramp it up. That's good. All right, well, this will be a little embarrassing. The first few minutes, it's going to be a little bit pedagogical, but you're probably, if you were in a quantum course, it was probably taught from a perspective of mathematics and wave mechanics and not so conceptual. And the topic of the day here is quantum computing, and it deals with something called quantum information, storing information quantum mechanically. And in fact, it's a much more natural way to teach quantum physics, especially to young people that know something about bits and computing information. And the math is still there, but it's hidden in a way that doesn't interfere with the very interesting and novel aspects of quantum, and that is superposition, entanglement, and so forth. So I'm going to spend a little time talking about that, and then as quick as I can jump into some particular hardware that we are developing to make quantum computers. And well, there's a picture. Those blue dots are individual atoms. Each one is the same isotope of the same element. It's 171 ytterbium, if you have to know. They're atomic ions. They're charged atoms, and that's why they form this crystal. They repel each other, but we also trap them. We push them together, so that compromise gives an equilibrium spacing of about a few microns, a few micrometers. They're obviously resolved optically. We're shining a laser beam on them, and you can see we have resolution to see them individually. Now, each atom is actually smaller than these dots, about 1,000 times smaller. The dots are blurry because of diffraction, so we well understand that. And so the total size of the string, it's been magnified here, is something like, I think that's 80 atoms, and so it's about 0.5 millimeter from left to right. And they are suspended, they're trapped on this device. It's actually made mostly of silicon, a bunch of electrodes. You can't see, there's about 100 electrodes here, like little diving boards. And these atoms are floating about 1/10 millimeter above the surface here. So the key here, and the key to all quantum mechanics, is isolation. Quantum mechanics only works when a system is well isolated, in a way. And so this technology represents the most extremely well-isolated quantum system in all of nature, I would say. Individual atoms, they're in a vacuum chamber. There's no air here. They're not part of a surface. They're not part of a solid. And we control them and make quantum gates to think about building future quantum computers that have certain properties that I'll get into in a minute. Okay? So with that quick introduction, I mean, you can tell I'm an experimentalist, not a theorist, but I'm going to talk a little bit about theory to motivate you on why quantum information is so interesting. And as you probably know, Singapore has an outsized posture on the world stage in quantum computing, quantum information. So that's probably why many of you have heard of this before. So I'm going to talk mostly about this platform from my work at the University of Maryland, which is just inside the Washington Beltway, and also this space is very startup looking, of course. So I will talk a little bit about our work at a startup company nearby called IonQ, and comment a little bit on that interaction. Okay, so here we go. Very broad introduction to the field, and most folks with scientific backgrounds, they know a little bit about information theory, but not so much about quantum. For this crowd, maybe it's the reverse, but information theory, quantum computing, in a sense, is a confluence of you might argue, two of the big scientific breakthroughs in the 20th century, and that is information theory and quantum physics. So information theory, especially to those of us that are physicists, this is something coming, maybe academic computer science folks have a little better background here. But for me, what's very interesting in the 20th century of information theory was the realization that information it's abstract, and it doesn't really matter what physical system stores that information. And of course, the abstract Turing machine is just a model of classical computing, where we imagine having information on a moving tape and a head that has memory that can do something to the bits on the tape, depending on what's in memory. And what Turing showed, and it's a very deep result, is that any classical computer can be modeled by this device. Of course, the clock speed and the particular operations are immaterial. You can always adapt to any type of classical computer. Now, no computers really look like that, so nobody's built a machine, really, a useful machine that looks exactly like that. But the point is that we've abstracted the idea of computing to some device that's independent of any hardware. And I think this is compounded by Shannon's theory of information, where he defines the bit, the binary digit, and in fact develops a mathematical relationship between information and the probability of occurrences of some alphabet. So the English language has 26 letters. If they were all equally likely, each letter would carry something like a little less than 5 bits of information, and that just comes from this formula. It's called the Shannon entropy. It quantified information in terms of bits, and with these results in the mid-20th century, society went on a quest to look for bits in nature to build devices. I know I'm sort of whitewashing lots of interesting history there, but this is basically what happened and why we have the information era in the 20th century, because we finally had a theory that said, well, a computer is independent of its hardware. It doesn't matter what you use to store it. So in the 1940s, during and after the war, there were vacuum tube computers that you've probably seen or heard of some of these. The British Colossus, Americans, the ENIAC, and the Russians had this thing called MESM that I only recently learned about. But they were made of vacuum tube elements as their transistors, in a way, as their switches. And vacuum tubes, of course, I'm gonna contradict myself later, because quantum computers these days, we're making them with vacuum tubes, but hold off that thought for a minute. Vacuum tubes for classical computers were pretty unreliable. They broke all the time. Well, they had many vacuum tubes. ENIAC, I think, had 10,000 of them, and there was even a full-time position for somebody to just replace broken vacuum tubes. And what happened, of course, in the 40s and 1950s is that vacuum tubes were replaced by the solid-state transistor. And if you look at this very famous, beautiful picture of the first solid-state transistor developed at Bell Labs in 1947, it looks even worse than the vacuum tube. And I guess it was. This thing was quite unreliable. It looks unreliable. I mean, it had. So what is this? This is a chunk of germanium down here, a semiconductor. This is a piece of glass that has gold, a gold strip, a ribbon on the bottom. And that gold strip, there had to be, I think, a little bit of water actually at the interface. And this spring here gives some amount of tension, of force, that makes this junction work. And when you run a current through this gate, you'll get some current that depends on that current going from the source to the drain, something like that. A three-pronged transistor. And of course, what's interesting about this device is it's solid state, and it's pretty clear that this, in the long run, maybe it wasn't clear at the time. It took many decades to really engineer this to the current, say, TTL logic systems that we have in our current CPUs, billions of these transistors. But because it's solid state, that made it interesting for companies to start to think about scaling these things up. The first processor, I think, only had 10 or so transistors, and it didn't have very many applications that sounded very interesting at the time. So I say that because quantum computing is in the same place that is right now. We don't have a whole lot of applications that we can see, but in a sense, we're going to build them anyway, and hopefully the applications will come. So the advent of solid-state electronics gave rise to, and again, I'm just giving highlights of the history here. Moore's law, which was the exponential, the exponential growth in computing power over the last many decades. And this is a picture of, this is a graph of the last few decades, a log linear plot, time, the year here, and this is the number of transistors relative to some year, 1978. And of course, we all know the law is starting to saturate. It's not growing as fast as it used to. This is actually for a simple reason. You can't make transistors infinitesimally small. If you follow this exponential line for the next few decades, they'll approach the size of individual molecules, individual atoms. And at that point, there is no way to shrink them ever more unless we have nuclear reactions, I guess, or splitting the atom in a processor. So that's not going to happen. So the end of Moore's law will happen soon. I think this is a little bit overhyped the way it's said, because there's still a lot of opportunity with current processors, and as you know, we're now there's much more innovation in software and how we wire together such processors. And I think there will be many advents in classical computing. But the fact that it's saturating because of quantum mechanics, in a sense, because of the granularity of matter, is pretty interesting. And it was something that Richard Feynman, I would say, he saw this a long time ago. So Richard Feynman, the well-known theorist who liked to tinker, he liked to consider technology and the limits of technology, he had this very famous quotation in a speech he gave it at a physics meeting in 1959, and I think he was very excited by solid-state electronics, and he imagined the day when that was shrunk down to individual atomic scales. And he says, when you shrink down to individual atoms as the circuit elements, there will be completely new opportunities for design. And so at that time, nobody knew, he didn't know what these opportunities would be. And the opportunities are, I think by now we know, it's quantum computing. We still don't know exactly what quantum computers will be used for 50 years from now. I don't think anybody can say that. But there's definitely a new opportunity, and I want to talk about that. So when you get to individual atoms, of course, the laws of physics are, in a sense, changed, which is weird in physics. In physics, we don't like to say, well, the laws of physics depend on how big your system is. And this is the conundrum in quantum that is not often stressed in quantum mechanics courses. So I'm going to go through that right now. What are these laws of quantum mechanics? And if you haven't had a quantum course, this is just a 5-minute version. Quantum mechanics in 5 minutes. Well, the way I think about it and the way I teach quantum mechanics is that quantum mechanics is composed of exactly 2 rules, and only 2 rules. And each of them by itself, each of these rules by themselves aren't so difficult. It's when you consider them together that it gets hard. Okay, so here are the 2 rules of quantum mechanics. Rule number 1, and you've probably heard this, that quantum mechanics describes things as being a wave. Everything's a wave. Well, what does that mean? Well, we'll get to rule number 2 to tell you what that means. But a wave, by its nature, is delocalized. A wave exists in many places at the same time, if you want to think about a wave in space. sound waves. You can experience multiple tones at the same time if you want. Or if you throw a rock in water, the wave, of course, occupies the entire body of water, the entire pool or pond. Well, when we apply quantum mechanics to information, we think of bits, and these bits become quantum bits. And if they're quantum, that means they have a wavelength character. So this is a poor version of a hydrogen atom, a single proton that is bound together with a single electron. So this is a single electron, and I've drawn it in a funny way that has two orbits, and yeah, the electron's circulating around very fast. But these two orbits are occupied at the same time because that electron is a wave. So no problem. I mean, we're used to wave theories in nature. We're pretty comfortable with sound waves, mechanical waves, even electromagnetic waves. So we have a existence wave here. The electron's in two places. I'll use the water bottle as my example. This water bottle in two places at the same time. Yeah, big deal. It just has a wave that has a crest here and a crest there. Well, yeah, it's a big deal because we don't experience anything like that in nature. I'll get to that in a minute. That's rule number 2. But let's just say rule number 1. It's a wave, and it has a wave equation. So in terms of a qubit, we have this is a little abstract notation. If you haven't seen it, the line and bracket mean that that's a quantum state. So this is sort of the information, the quantum information. 0 and 1 mean we've identified some attribute of the system with 0 and 1. So this is 0 and this is 1, if you want. And so superposition means that we have both of those present. This plus sign is not the plus sign you're used to in arithmetic. This just means superposition of these two. A and B are important. These are the weightings of the superposition. It could be 50-50 or 90-10 or 80-20. Okay? And that's where all the math comes in. A and B follow a wave equation. So it could go from a 50-50 superposition to a 100-0 to 90-10. And A and B are what we control. We push them around, we manipulate them to change the type of superposition. And there's the wave equation. I won't talk about this math much. This is called the Schrödinger equation, and this operator is called the Hamiltonian operator. It has to do with the energy of the system. It's what we control. So when we play around with this H operator, we can state and change A and B if you want. Okay, it's math. It's only math though. The math is actually not that hard. It's no harder than any wave equation math. In fact, it's easier than some wave equation math, like this one. So you know this picture here. So the equation for surface waves on water is nonlinear. It's really complicated. And these are the equations that for some, I don't think that would work for this wave. These are for shallow waves and so forth. And it's pretty nasty stuff. And when you solve fluid mechanics problems like this, you need high-performance computers just to do that. So my point here is that you're not going to really get too much understanding of the wave by doing all the math. We have to be able to do the math, but you're not going to understand the concepts of quantum information just from wave mechanics. Okay, so A and B have math. Okay, so what's wrong with rule number 1? Of course, what's wrong is that we never experience superpositions in life. We never see things in two places. And so that's a problem. So we have to invent this other rule, rule number 2, and this is a little bit tongue-in-cheek, but rule number 2 says that rule number 1 only works when you're not looking. So it sort of answers the problem. It says, well, yeah, there are superpositions, but they only exist when you're not looking. That's one way to think about the second rule. This is a little weird. It's more than a little weird. But I guess many physicists don't like this setup because you can't derive rule number 1 from 2, you can't derive 2 from 1. They seem to be totally exclusive. And in physics, we hate that. You know, physics we think of as the king of science. Everything comes from one law up here, like force equals mass times acceleration, and all of mechanics comes from that. Even if it's hard to make that connection, at least in our mind, we have a logical sort of organization. In quantum mechanics, you can't do that. Or if maybe I'll comment a little on, you can do that, but you'll go crazy with other issues. So the so-called Copenhagen interpretation, kind of codified by Niels Bohr, is this approach that just don't think about it too much. We can apply rule number 1 and we can apply rule number 2. Well, we have to look at a system eventually, and rule number 2 says that when we do look, the system, of course, evolves into a particular state. So we're never going to experience a superposition. We see one or the other. And of course, the probability of seeing one or the other is given by A and B. Now, I didn't mention this, but A can be negative. A and B can be negative. In fact, they're complex numbers. That's sort of a detail. You may have noticed in the math, the wave equation has an I, so it's actually a complex wave function. But A and B, once you take the modulus square of them, they're real numbers, and they are probabilities. So A and B tell you about the probabilities, okay? Now, to me, what's strange about rule number 2, well, there's two things that are strange. One, it seems that by looking at something, you change it. And there's no other phenomenon in physics, any of science, that has that. We tend to think of things as happening whether or not we look at it. Maybe we didn't get the information, maybe we have ignorance. But when you look at it in quantum physics, the thing changes. Another way to cast that, in my mind, the more fundamental thing that's weird about rule number 2 are probabilities. Where do they come from? Probabilities, we're all comfortable with using probabilities to predict the weather, to estimate the weather, the stock market, or what happens when you flip a coin. But in those cases, the probabilities are used because we're ignorant. We don't know exactly what's going on in the upper atmosphere. We don't know exactly who's buying and selling what stock. We don't know exactly how hard we toss the coin. So we use probabilities. It's very useful, very powerful. But in quantum mechanics, it's not about ignorance. It's about we have to. We just have to use probabilities. And so a lot of people think of quantum mechanics as has a sort of mystic nature to it because its probabilities, somebody's cooking the books. You know, Einstein famously said, God does not play dice. Einstein hated quantum mechanics. He hated the fact that you had these two laws that we couldn't reconcile. That wave equation I showed, that's Schrodinger's wave equation, he also was puzzled by many aspects, and he invented this very funny experiment you've probably heard of, a thought experiment called Schrodinger's cat, where he imagines extending a superposition within a single atom to a big superposition. So here we have an atom somehow put in a superposition. It's like a radioactive atom. After one half-life, it's in a superposition of undecayed and decayed. And if you hook this thing up to a hammer that smashes a flask of poison, after a half-life, the atom is in a superposition, and so is the cat. The cat's alive and dead at the same time, so we can actually write this. If we wanted to ascribe the livelihood of a cat to a quantum state, we would write it this way. It's a superposition of undecayed atom, atom alive, and decayed atom, cat dead. So Schrodinger, this paper, by the way, it's almost unreadable. It's like a 50-page treatise, and he has one paragraph, and he calls this a quite ridiculous case. In other words, this is weird. This can't be the final word. Well, as far as we know, it is. If there is a final word, it's at least as confounding. One way to resolve rule number 1 and number 2 is the so-called many worlds, or the many universes interpretation. And this says that when we make a measurement, what happens is the universe actually splits. So we see the one that we see, whatever it is, and in the other universe we see the other version. Now the problem with many universes, I guess there's some. I don't want to comment on it because it's an interpretation. It's not really scientific. But what decides these probabilities? That's still an issue. How do we know what universe we're in? Anyway, it's interesting night reading. There's a lot of popular books on this, and I recommend. They're a lot of fun to read. But if during the day we use rule number 1 and rule number 2 and probabilities. Okay, that goes a long way. So to belabor the point here, there's only one analogy I can see here to the idea of superposition and this type of state. It's called an entangled superposition, and I want to talk a little bit about that. And we're going to start to add qubits together, see what quantum computers can do, and then build one. That's the job we have here for the next half hour or so. Okay, so this is an analogy that sort of gives you an idea. If you've had no background in quantum, you could maybe have an analogy to what a superposition is. So here I've drawn a cube with ambiguous perspective because these lines are parallel. So which face of that cube is the front? Is it this lower left face, or is it the upper right face? Well, you can sort of see both. So it's sort of like a superposition, and when your mind locks onto one perspective, it typically stays there. And so that's like a measurement, maybe. And then close your eyes and do it again, maybe you'll see the other one, okay? It's a weak analogy, and these are the two definite perspectives. Now, what's cool about this analogy is that it works for multiple qubits. So if we have two cubes next to each other, you'll probably find that both faces have the same perspective. But individually, they're totally random. Close your eyes, shake your head, and do it again, and you'll maybe see the two other perspectives. This is a little like an entangled superposition. And entanglement is basically the currency behind quantum computers. It's what gives them their power, and I'll comment a little more on that. And the reason it is that entanglement is a correlation that is something you could never have in a classical system. It's sort of like having a wire without a wire. And this, again, this is one way to think of the power of quantum computing. They can be automatically wired up in ways that are super complex that you could never do with real wires. Now, this analogy breaks apart when you separate the cubes because they become independent, but quantum mechanically that's not the case. Quantum entanglement can persist over arbitrarily long distances, and so this idea of entanglement was the basis for Einstein's rejection of quantum mechanics entirely. He thought there had to be a greater theory overall because of states like this. So this is an entangled state, and you'll notice the amplitudes are 1 over root 2, because when you square 1 over root 2, you get 50%. So this is a 50-50 superposition of two states involving two qubits, a red one and a blue one. They're prepared in a superposition of 0, 0, and 1, 1. Okay? And remember rule number 2, when you measure this superposition, when you measure either qubit, if I measure the red one and I get 0, I know immediately that the blue one is 0. I don't even have to look at it. That blue one could be on the moon. When I look at my red one and I see 0, I know immediately that the one on the moon is the same state. Even faster than light could traverse the distance between me and the moon. And this is what bothered Einstein. It seemed to violate his theory of relativity, which by then, even in 35, was firmly established. It seemed like there's communication faster than light here. Well, the resolution to this so-called EPR paradox, Einstein-Podolsky-Rosen, is that if you do this many times with many sets of red and blue qubits, and the blue's on the moon, the red's here, and we prepare this same state over and over again with many different sets of qubits, I'm just going to get random numbers, because half the time I'm going to get a 0, half I get a 1. And it's true that you have the same random numbers on the moon, and they're perfectly correlated, but random numbers contain no information. So there's no information traveling faster than light. That's the resolution, and it has to do with Shannon's information theory. Okay? All right, so no problem with entanglement, fundamentally. It's still kind of weird. And there seems to be this, I quoted him here, spooky action at a distance. There certainly is something between these qubits, independent of distance. So now let's put more qubits together and build a quantum computer. And I like to think of this as a good news, good news story. And the first piece of good news is that when you put lots of qubits together, the state space explodes exponentially. Because every time you add a qubit, you've doubled the number of possibilities. Okay? So this is 3 qubits, so there are 8 possibilities. Here's the quantum state of 3 qubits with 8, these are called amplitudes. When we square them, they're probabilities. So there are 8 of these amplitudes. Now, 8's not that big. If I add a qubit, there's 16, 32, 64. If we put several hundred qubits together, the numbers get so big so fast that with merely 300 qubits, there are more configurations than there are atoms in the universe. Okay, so this is wildly good news. There's sort of quantum mechanics has its own exponential, if you want. Now, don't call this a Moore's law, because it's very hard to take advantage of this exponential explosion. It's because of the bad news. When you look at this superposition, you may have computed some function in parallel, massive parallel, but when you look at it, you only get one answer, and worse still, that one answer is completely random. So it gives you almost nothing useful. To find out what this is good for, you have to invert the function and find the input. You might as well just do it serially for all the inputs as you would do in a classical computer. Okay? So that's really bad news. I'm sure Feynman realized this in 1959, that simply computing in parallel is not good enough. The final piece of good news that really has evolved into what we now call quantum computing was only realized a few decades ago, and I would say David Deutsch is the champion here. He realized that these amplitudes follow a wave equation, so they can interfere. They can interfere constructively or destructively, just like any wave. Now, a destructive interference in a quantum wave is interesting because the existence of something can destructively interfere. That's a little weird, but it's just a wave equation, and if we're going to use a wave equation, we have to admit the possibility of interference. So Deutsch imagined having, it's very hard to draw this, but you imagine these amplitudes evolving in time here. Here's space, the number of qubits maybe, and here's time. We have these red dots, these are quantum gates that allow interferences to be controlled in a certain way from the outside. And you can imagine certain circuits, certain patterns of gates where you only get one answer at the end, only one, and all the others they destructively interfere. And in this situation, it looks like we make the measurement, but no, there's no measurement. This answer depended on the circuit, and it also depends on all these inputs. So if an algorithm can be cast in this form, it's very interesting because it could deal with an amount of information that you could never deal with classically. With just 300 qubits, if you don't need 2 to the 300 operations, if you can find an algorithm that scales well, you could use this device to calculate something you could never do otherwise. Okay? So that's really good news, and it's very subtle to put this to use and to find the algorithms that are useful. There are a few out there. Most famously is the Shor algorithm for factoring large numbers, and this in the mid-90s really put quantum computing on the map as we know it today. So Peter Shor showed that the number factoring problem, which classically scales exponentially with the size of the qubit. The best known algorithms are still exponentially hard. It turns out if you have a quantum computer, you can factor in polynomial time, meaning exponentially faster than you could using the best algorithms. And so, factoring for small numbers by inspection, it's easy, but when the number gets really big with a few thousand digits, for instance, it's impossible. You just can't do it. The nice thing about this algorithm is that you can check it very easily. If you factored a number, it's easy to multiply them back together, the factors, to see that it worked. And so the way this is a very almost too simplified version of how it works. But the idea is, if I want to factor a number, I store a superposition of lots of numbers. If I write this in binary, this would require, I guess, 6 qubits. That would give us 64 states. So we prepare a superposition of, say, the first 39, and we develop an algorithm. I won't show you how to do it. It's well defined how to do this. And it's a polynomial algorithm, so you don't need too many gates. The wave function evolves to this. It's sort of a forcing function, and the answer now, if you measure this quantum state, you either get 13 or 3, these are one of the factors of the number you're trying to factor. Of course, the structure of the algorithm depends on the number you're trying to factor. So this is the art of doing the algorithm. So this is a very clear example of quantum computing at its best, because there's no uncertainty here. There is uncertainty. You don't know if you're going to measure 3 or 13, but it's a bright line. Quantum computing is good for something. Okay, so this is the mid-90s, and I think the problem, well, unfortunately, factoring is a really hard problem. If you want to factor a few thousand bit number, you need tens of thousands of qubits, and you probably need, unfortunately, 1 billion operations. So the operations, if they're not better than a part per billion, then the whole thing will, the noise will take it away. So you need to do something called error correction, which I don't have time to talk about. You might know a little bit about it. Error correction requires more qubits, even more. So instead of 10,000 qubits and 1 billion operations, it might be 1 million qubits and 1 trillion operations. I mean, it's really hard. Way away from what we can do today. Fortunately, there are other algorithms that we're starting to get hints at, and I want to point you to the fact that quantum computers, they find some global output that depends on lots of inputs. So look for problems like that. Problems that have global output that depends on lots of inputs, and to me, this is a little bit of a catch-all type application, but optimization is exactly like that. This is a very simple optimization problem. It only has 2 inputs, x1 and x2. Where's the minimum? Well, you can just look at it and see it. Right? Yeah, so minimizing this very complex function of x1 and x2, because there's only 2 dimensions, it's easy to see. But imagine if we had 1,000 dimensions, a function of 1,000 variables. What value of those variables minimizes this nonlinear function? Well, that's a really hard problem. You have to, I mean, one way is to brute force evaluate every possible input, exponentially many inputs. Can we devise a quantum algorithm to somehow do that faster? Unknown in general. My guess is that the answer is no, but we can find a quantum algorithm that might approximate the optimal value, and it might approximate it better than any classical algorithm could. So it's very hard to prove things if they're approximations. So in a sense, this is one of those examples. We need to build it and just test it out and see what happens. That sounds a little wishy-washy, I'm afraid. But optimization is, of course, all over everything we do. A lot of you probably know a lot more about optimization than I do. It's a huge software problem, finding optimal values of models, complex models. And these are 2 examples of optimizers. To me, they're sort of the same thing. How is molecular physics in the traveling salesman problem the same thing? Well, in molecular simulation, you take a molecule like this one. That's TNT, by the way. TNT has, I think, it has mass 230 or something. A lot of electrons, 230 electrons. Those electrons optimize their energy. They minimize their energy, and that determines what they do on this molecule. If we can calculate what that minimum energy is, we can say something about its reactivity with other reagents. We can develop maybe new catalysis processes. There's a huge market here if we could calculate ground states of complex molecules. Oil and gas industry would be very interested in this, of course. Not to mention drug discovery, big pharma, and so forth. Again, I don't know exactly what I'm talking about here, where the applications are, but I'm told that even a simple molecule like TNT, we can't calculate the ground state. And a quantum computer might be able to do this. The traveling salesman problem, you probably know, is one of the most famous combinatoric problems. Here we have some number of cities on a map. So let's say there's 100 cities on the map. What's the shortest path visiting every city exactly once? Well, there are too many combinations, too many configurations. So classically, we have approximate versions, heuristics that can solve this. They're pretty good, actually. And it may be that a quantum system, if we can encode a cost function in a Hamiltonian with a bunch of interacting qubits, we might be able to program the device to do something like this. So, models, quantum computers will solve models. Quantum computers are not big data machines. When you measure a quantum computer, you get one answer, only one bit string. And the inputs are also pretty simple. Like the number of qubits you have, there's just an input for each qubit. It's not about big data, it's about big configuration space. And models can be very simply written down. They can have huge configuration space. And this is where quantum computing may have some applications. This article is from last year. It had nothing to do with quantum computing, actually. It was just talking about models and how to solve them. They talk about the Netflix algorithm, the recommendation for the next movie you want to see on Netflix. It's an optimization problem. And so, lots of people in all sectors of the economy are looking at quantum computing to better optimize their problem. From financial markets to big pharma, as I mentioned before, and so forth. Logistics. The traveling salesman problem is obviously an important one if you're FedEx, for instance, or you're a Department of Defense, and you have these issues. Okay. So with that, I'm finally going to talk about building one, and we have a lot of the hints on what we need to do to build a quantum computer, and it really has to do with rule number 2, avoiding rule number 2 until we want to measure the system, and this isolation. We're going to be looking for isolated systems. So I'm going to quote my colleague Bill Phillips at Maryland. So he's one of the inventors of laser cooling and Nobel laureate from 1997. He's fond of saying that a quantum computer is more different than a classical computer than a classical computer is from an abacus. And what he means is that the rules that govern these 2 machines, they're both Turing machines. They have the same abstract rules. One's a lot faster than the other. They look a lot different, but they're fundamentally the same. These 2 are fundamentally different. And the corollary, I would say, to his quote is that why should we expect quantum computers to look anything like a classical computer? They're so fundamentally different. So there are a number of technologies that are looking interesting for building quantum computers, and they're all exotic. This is a figure from a review in Science from a few years ago. I've had to update the companies that are playing around with these. That's evolving. But I would say largely the top two are the ones that are being built into systems right now. They're the most advanced. And they include superconducting loops, superconducting qubit circuits, and individual trapped atomic ions. They couldn't be any different, any more different than they are, right? Of course, you've heard of Google and IBM and their boxing match to one-up each other to build big quantum computers, and there's some startups involved in that field as well. I'll talk a little bit about our startup IonQ, but also Honeywell has taken a posture at trapped ion quantum computing. Some of these other technologies, they're beautiful research right now, but they're research. Nobody knows how to build a system out of any of these things right now. It's great research in the laboratories here in Singapore and elsewhere, but there's no way to build a system with even a few qubits in these technologies yet, including silicon. I don't think it looks good for silicon to build a really big device. I think we need breakthroughs. We need really great research to continue there. And this is despite the fact that you have some pretty big, at least in the US, these are very big companies investing in this. Okay, back to that figure. How do we make a quantum computer out of this? Well, turns out that these individual atoms form wonderful qubits. In fact, they're atomic clocks. They're perfectly replicable. Every atom is exactly the same. They're the same to 13 digits easily. If you really need 18 digits, you can do that too. In fact, there's a lab at NUS, Murray Barrett makes clocks that are about a good to a part in 10 to the 17, maybe a part in 10 to the 18, give them a few years. So they're much better than we need in terms of replicability. So that's one recipe for scaling. You better be able to have the same qubit again and again. You don't want to have to worry about defects in the system. So the qubits are great. We understand them. There's nothing new there. But how do we make entangling gates? How do we entangle states to do these gates that are the foundations of any algorithm? Well, we can do that too because these atoms are charged, and if we pluck one of the atoms with a laser beam, the other atoms are going to know about it, right? It's very much like plucking a guitar string. And we pluck these atoms with laser beams. So the physics, there's some equations here, I'll go quickly through it, but if we have a line of atoms like this, the trick is we're going to say we want to entangle any pair of atoms in this collection. If we shine laser beams on those particular atoms in a very funny type of way that pushes the atoms around, these are called optical tweezers, but the force on the atom depends on the qubit state. So if the qubit is in the state 1, it moves up. If it's in the state 0, it moves down. So if we hit two atoms with two laser beams, in general, they're going to be put in a superposition of position. If we have a superposition of 0 plus 1, 50-50 superposition, we apply this laser beam, the atom actually splits into two pieces. The atom's in two places at the same time. So is this atom. It's in two places at the same time, and they feel each other's charge moving around. And when we do this, there's a pulse of light that does this. This is a little detailed. We get a quantum logic gate. It's called an Ising gate. It has parameters in it. These gates have been operated with 99.9% accuracy, and they're not super fast for a computer, but they're on the order of tens of microseconds. Okay? What's important is we can do this between any pair of ions, any pair of qubits. It's a fully connected system. It looks 1D, doesn't it? No. This is not a 1D collection of qubits. In space, it's 1D. But the interaction graph is multi-dimensional because it's fully connected. And that's actually important if you want to compile an algorithm and make it work efficiently. So here's an animation of how this works in the lab. We have actually a bunch of laser beams, and this is a very interesting. Let me back up a little bit. Uh-oh, this always happens. Oh, did it work? So this is an optical device that splits beams, and we have individual control of every one of these beams, their frequency, so we can pluck these atoms in any way we want. And when we execute a circuit, space and time goes to the right. We have these are just 4 qubits in the circuit, but we have a lot of qubits here. When we want to do an entangling gate, we hit the 2 ions we want. They get entangled, then we might affect just 1 qubit to make a superposition, entangle these 2, and so on and so forth. So you can realize any quantum algorithm you want, in principle, by shining a bunch of lasers and having them timed with the right parameters. And at the end of the day, we make a measurement of the qubits, and this is actually very direct in these atomic systems. The atoms that glow are 1, and the atoms that don't are 0. So we just count which ones are bright, which ones are dark, and that gives us our readout. And these readout fidelities they can be 4 or 5 nines of efficiency. In other words, the readouts are very clean. Now that's hard to do in quantum. Usually in quantum we've isolated our system so well that we can't get information out. But by shining laser beams on these atoms, we can do both. Okay, so simple as that. Build a quantum computer. Well, the problem with the infrastructure surrounding some of these trapped ion machines looks something like, this is a typical university lab where every mirror, every laser is perfectly adjustable, all the axes and so forth. But we're not engineers at the university. We're building a system. This is a research laboratory. And in fact, Dmitry Matskevich is in the audience. He used to work in this lab. He recognizes it well in Maryland. And there are actually 3 groups that are here at NUS that are, I would say 4 groups that are playing with individual atoms at this level, with possible clocks and quantum computers. And if you visit these labs, they're complex. And most people in my field, unfortunately, are very proud of pictures like this. I'm kind of embarrassed. I hate this. This is what makes life so hard in this platform, the complexity. All that electronics, all these lasers, simply to control the lasers that we shine in these atoms. And it should remind you of this will showed you before, right? It's unwieldy, very hard to think about that. Well, the good news is, if you know what you want to build, if you know what you want to do, you can nail down a lot of this stuff and simplify it dramatically. So without much exaggeration, everything you see here, except the students, they're not inside the box. Actually, it was a little bit of an afterthought. The students don't even need to be in this room to run this thing. This black box is about 1 meter cubed. Everything we need to adjust is automated. It has actuators, all electronically controlled. And we don't have to open this box but every several months. And so everything we run from somewhere else. And this system obviously is a lot more stable. Everything is smaller, and it has that those individual laser beams I showed you. That's sort of the heart and soul that goes on in here. There's a lot of electronics that is outside this box that doesn't need to be shrunk and so forth. But the critical stuff, which is most of this actually, is inside that box. And all the electronics is out. It also has been compressed somewhat, but the stuff that really matters. The vacuum chamber with the chip and the individual atoms are inside there. And one thing that was interesting, a few years ago, we built our first generation of this device. Not this one, but the one before it, which looked a little more like this lab. And we had control of about 5 qubits to start with. Full control, though. All right, 5 is not very big. So everything we did there, we can simulate. That's what I hate sometimes in physics. Almost everything we measure, we know what the answer is going to be. And if we don't get the answer, we assume something's wrong with the experiment. So it's a little bit boring. But we wouldn't be in this business if we didn't think we could scale this up to a few hundred qubits where we can't predict the answer. So when we built our first device, people, it was interesting timing. IBM had just unveiled their so-called quantum experience. They put 5 superconducting qubits on the cloud. 5, same numbers we have here. And people started using the IBM system, and to their credit, it really brought quantum computing to the masses. People, high school students, could program a quantum computer. They couldn't get much out of it because the IBM system is very poorly performing. They couldn't do very many gates. Our system could do a lot of gates. So these same people, many of them came to us. We'd love to run some algorithms on your machine. Can we do that? that was an interesting model of research. We started looking like a user facility. In fact, over the last few years, there have been so many folks that have come to us, and it's like going to school again. I've learned so much condensed matter physics, even some high energy physics and nuclear physics, and even a little bit in black holes, believe it or not. Maybe I have time to talk about that. But one of the first folks that approached us was from Microsoft. Martin Rottler is a computer scientist. And in this reference here, in 2017, he had a bunch of algorithms and wanted to compare with the IBM system. And the IBM people were saying, they were great. This is wonderful, let's do it. And so, we wrote that paper. It was a lot of fun. Totally different. Remember I showed you that Shannon and Turing, the notion of a computer should be independent of its hardware. Here we had two totally different types of computers running the same algorithm. Kind of neat. I don't have too much time to talk about everything here. I think I'm going to skip through the scrambling one. Let me do it. This is kind of fun. So Norm Yao and Benny Yoshida approached us and said, you guys can run a circuit that can test whether a certain quantum process scrambles or not. Now, scrambling is sort of like super entanglement. It spreads the information all throughout the space of all the qubits. And it's thought to be the process that happens when you put a qubit into a black hole. It scrambles with everything in the black hole. If you could imagine a black hole being a quantum process. Well, a black hole is closed, so it's sort of like rule number one, and if a black hole is closed and isolated, then why not think of it as a quantum process? So they came up with this circuit where this unitary operation, this is the thing that scrambles, and we have to implement this, and it's inverse in time. We have to go backwards in time in a way. And it's a circuit, so we can do this. We can write down those circuits. And the idea here is that these two operators are sort of like black holes. One's a forward black hole, and the other's black hole spinning in the opposite direction, if you want. And the idea in this circuit is we have inputs. This is 7 qubits. We put some unknown quantum state here, and if this is a scrambling operation between these three, and this is the perfect copy, then this state actually appears here. It's called teleportation, actually. That state appears here based on some measurements. I won't get into the details. But it was kind of cool. We had this circuit machine, and we're testing some very fundamental, very trivial example of something having to do with black holes. So that was kind of neat. Here's what U is. I don't want to get into the details, but it has tunable parameters that we can tune to make it, we can tune the amount of scrambling, and indeed, when we tune the amount of scrambling, the teleportation fidelity goes up. When it's 50%, it's sub-threshold. It doesn't, if you only have a teleportation fidelity of 50% of a single qubit, you didn't teleport it. If it's above 50%, then it has some aspect of teleportation. So that's one example. Another example of an experiment, this came to us from a few folks in condensed matter, was the idea of studying a phase transition in magnetism. And I'm just going to go very quickly here. So we implement this Hamiltonian, not using a circuit, but we actually hit all laser beams on all the time with lots and lots of qubits. And in the end, we measured the size of the largest domain in each run of the experiment, and we saw sort of a kink, a minimum in that domain size, mimicking a phase transition. And the important thing is that this data was 53 qubits. 2 to the 53 is pretty big, and we can't calculate. We could not calculate beforehand where that kink was going to be. I'm not saying this is a novel magnetic material that we should find in nature, but this is a mathematical problem that we couldn't solve. And in a sense, this quantum simulator, a restricted version of a quantum computer, did it for us with a lot of qubits. Now, we didn't have full control over these 53 qubits. It was more of a global type interaction. Okay, so what about I and Q, now that I'm wrapping up? Well, I showed you the big black box. What's missing is that big black box is at a university, and we don't have a very advanced controller or software stack to deal with that big black box because we're a university. We can't hire, we can't afford to hire engineers to work on one thing for many years at a time, certainly the software stack. So we took the mechanical design of the hardware and dotted all our I's, crossed all our T's, and made sure that intellectual property was clean and so forth, and formed a company called IonQ that added the upper level of the quantum computer stack to very similar types of hardware. We've built 4 systems at IonQ so far, kind of quietly. We're just starting to sort of publish results and so forth. But this is system number 1. There's a vacuum chamber inside there. And the controller, this is part of the FPGA controller on the side, and there's a few other lasers over there. Systems 2 and 3 can't see very well. These are totally shielded. And system 4 is on the way right now. Right now we're running system 2 and 3 pretty much around the clock, kind of testing it out, testing the automation and running algorithms. As an example of the automation, you might ask, how do you load these atoms in that chip anyway? Well, when we do it, the atoms stick around for a long time. I've failed to mention that. They can, again, there's complicated answers to this, but they stick around for at least 10 minutes, could be 10 hours. It really depends on the system and the environment. But loading them can be pretty fast. And this silicon chip trap I showed you has many electrodes. In fact, when we load from a loading slot on this side of the chip, and we shuttle one by one. This is a real-time image of load one atom at a time. It appears here, we photoionize it, and we channel it over here, we merge with the existing crystal there. And the software, we ask for 24 ions. And as soon as we get 24, we go. And that was real time. So it takes less than a minute to load these. That's a very, very, very stable system. Something very hard to do that at the university, to have image, to have software that recognizes the pattern and act on it in a fast way. It's part of a system. I use that word a lot. It's not really physics anymore. It's not atomic physics. That's at the core here, but it's a system on top of it. That's the part we're doing at IonQ. Now, at IonQ, we've been playing with some benchmark algorithms. This is a simple version of an algorithm called the Bernstein-Vazirani algorithm. It's with 11 qubits. I won't get into the details. It's an oracle where we're getting hidden information in some small number of trials. We've also run a quantum simulation of a very small molecule, that of water. Water only has 10 electrons, and so it's a simple circuit to do this, and there's a couple of references here in the archive if you're interested. Again, nothing to write home about except that we're sort of posting results and we know how to scale in the future. Now, I want to talk for just a few minutes before wrapping up about scaling. I've shown you data and systems with dozens of qubits here, but we need to have a path to thousands, tens of thousands of qubits to do something interesting. Remember, the factoring algorithm probably requires millions of qubits. How are we going to hope to scale this system? It's not a solid-state system. Individual atoms, are we really going to put load a million atoms one at a time? Well, yes and no. I think the yes part is yes, we have to have a million atoms, but the no part is that we don't have to put them all in one trap. In fact, I would argue that any scalable quantum computer has to be modular. I might even be more general and say anything that's complex has to be modular, period. And so here's an example of modularity. We see that naturally in airline traffic. You're not going to be able to fly between every possible city. That would be stupid economically. So we have hubs, and we have sort of a modular network that's derived from that. With trapped ions, we have two technology trains that are coming along that are going to allow us to scale up in a modular way. The first one, imagine we have all these atoms, and you can think of this as a tape, and we have laser beams that might be like a head. Well, you can imagine having a line, lots and lots of atoms, and actually move them around. Just move them around, and do your algorithm, move them around. Now, you don't have full connection anymore. But if you're going to go modular, you're already abandoning full connections. That's what a modular architecture is. It's like a multi-core processor. You've decided to grow the system, I have to limit the connectivity. That's what it is to be modular. A more advanced version of shuttling ions around is to actually turn corners and have separate zones. And my colleague Dave Wineland and I thought about this a long time ago, and there's steady progress being made here. And this, I think, will get us to hundreds to maybe even 1,000 or a few thousand ions, maybe even on one chip. But in the long run, we probably want to go off chip. And the great news about these trapped ions and most atomic systems is that they're optically active. We can move the information through photons, single photons, that can go through fibers and fiber switch networks. The idea in this concept here is that each of these red boxes might be 100 ions, where we have full or near full connectivity, but then maybe one or a few of these ions can release information through photons, and depending on the configuration of this switch, and I don't get into the details of what happens here, photons interfere when certain pixels fire on this camera, on this 2D camera here. Depending on the configuration of the switch, any pair of ions can be entangled at a distance, off chip. All the basics of that type of architecture have been demonstrated from one-to-one, remote entanglement between trapped atomic ions. Scaling this up and the optical engineering needed here is going to be a great challenge, but there's no breakthroughs required. This is not physics anymore. It's really about packaging, integrating photonics with these ion trap chips, and I know there's some great work here at NTU, the Disruptive Photonic Center, that is very much interested in this. And there's a picture of sort of a silicon waveguide that might be integrated with our silicon chips to do this in the future. It's very hard to do that at a university, of course. So that nasty picture I showed you with all the cables and so forth, this is actually a close-up of part of it. This experiment actually did exactly that. It moved information from one chip to another. This is, Dimitri will recognize this even more. He did part of this experiment where we took an unknown superposition here and teleported it over here, which is a fancy way of saying we just moved the quantum state. We didn't move any mass. We just moved the quantum state from one atom to another. It's called teleportation, but it's basically it'll be the fundamentals behind a modular quantum network in this platform. So that state appears over here. Okay, last slide. So this picture I borrowed from Hartmut Nevin at Google. It's the famous number of qubits, number of gates plot. You obviously want to be up and to the right. You want lots of qubits, lots of gates. To do Shor's factoring algorithm, you might need, like I said, millions of qubits, actually maybe many more gates, maybe over here. Now, this red line is called the quantum supremacy line. If you're above the red line anywhere, if you're in the white here or blue, you can't simulate it classically. And this might budge up very slowly due to Moore's law, but not much. Okay? Now, ion traps, we're doing okay. We're starting to push on that line. Some of the systems with less control, quantum simulations, this is the 53 ions I told you about before, expressing it in terms of gates. But we're steadily marching up, and it's easy to project future points in this aggressive way. But again, I don't see any fundamental reasons we'll have not getting to these landmarks. There's lots of engineering that has to happen. No new physics, though. So I'm pretty confident that we'll be able to break through that line. Doesn't mean that we'll do anything interesting. It means that we'll do something you can't simulate classically. That's necessary but not sufficient. So we really need to keep marching. And at some point we're going to have to do error correction, where I think at about the 10 to the minus 4, at the 10 to the 4 level, there are fundamental errors that occur at the 10 parts per million or something in our system. So at that point, if we want to do more than 100,000 gates, we're probably going to have to do error correction. So that's a whole nother topic, of course. But with trapped atomic ions and atomic systems, we don't have to think about error correction yet. I think we could blast through this quantum supremacy. Now, one thing I am worried about in the superconducting race, they're building more qubits, but they're actually getting smaller numbers of gates. So they're moving like this. And if they move like that, they're never going to do anything interesting. That's what's happening right now in most of the superconducting work that we've seen. In fact, a lot of the solid-state work is following along. Silicon spins are like that too. They need breakthroughs to make this turn. One of those breakthroughs might be topological qubits. That's kind of futuristic, but there's some interesting physics there. So with that word, topological, I borrowed this figure from the cover of MIT Tech Review. It was, the context here was the blockchain, actually, but it could easily have been quantum computing. Yeah, there's hope, and there's a lot of hype, but the hope is interesting because there are problems out there that will never be solved without quantum computers. There's not enough space in the universe. That sounds dramatic, but that's not really hype to that statement. It doesn't mean we'll do anything. It just means there are problems out there. We may never get to those problems, But if we do, it will involve quantum computing. And of course, there's a worldwide, this is my last slide. There's a huge worldwide effort in bringing the workforce together from university researchers where we know quantum mechanics and are very comfortable with it, to bringing that to industry where they're not so comfortable with quantum yet, but they build things. So each community has something the other wants. And bridging those communities is something that governments can do. And so this is one reason why most governments that are interested in science and engineering are putting a lot of effort into this. And I think here in Singapore, it's really outsized per capita, the effort in quantum computing. And this is typified by the CQT at NUS and what's happening at A-STAR and at other agencies in the government here. So yeah, this is you can tell where this came from. This is from a Nature report a few years ago. It's even outdated now. Me? Yeah, maybe this is order of magnitude in China. Yeah, they've really grown. But yeah, even in the US, of course, we have our own national quantum initiative. Again, to me, it's about workforce. And at INQ, this is an old picture. We have now about 40 employees. What most interesting to me is that only about a third of these employees are like me, atomic quantum physicists. The others are professionals. They're software developers, FPGA designers. They're there for a reason. They want to know about quantum computing. They sort of believe in this vision. And getting all these people together and interacting at this small company, it's amazing. It's the best part about that company, because they're doing things that we could never do at university. And this is, to me, what any national quantum initiative would be about. And I mean, I know this area here in Singapore, I think is a beautiful breeding ground for exactly that. And there's some nice startups in the quantum field right here in this building or nearby, and that's great. I also have a research group at the university. I was actually CEO of INQ for about 9 months. That fortunately stopped a few months ago. We have a real person there now who knows business, but also knows AI and has an intellectual mind for things. He was formerly the chief engineer of Amazon Prime, actually. So I'm back at the university now doing research, especially in some of these scaling plans that INQ can't do yet, that we hope to translate that technology over to the company in the future. Both places we're actively looking for people, so if you're interested in coming to the Washington area, please let me know. Thanks for your attention. I went a little over time, but if there are any questions, if we have time, do we have time?
Hello, very basic question. What's the temperature of the silicon chip?
The temperature of the
silicon chip.
Oh, yeah, good question. I'm glad you brought that up. It's all room temperature. Well, that shouldn't be a surprise. It's in a vacuum chamber. So the chip can be at room temperature. The atoms are 1/10 of a millimeter above the chip, so the atoms are laser cooled. The atoms are very cold, but it doesn't require a refrigerator. It's a very small amount of matter in these atoms. So laser cooling keeps them sort of motionless. There is, when we get to 10 to the minus 4, 99.99%, the thermal fluctuations in the surfaces of these electrodes will play a role. So we probably want to go to 4 Kelvin in the long run. We don't need to go to 40 millikelvin though. Going to 4 Kelvin will be just fine. On the other hand, if we only need to scale to 50 ions per chip, room temperature might be just fine. Yeah, this all runs on wall power. I mean, it's a pretty efficient system in terms of energy. Travis, maybe you can yell.
Just a quick question. So you show that you could entangle atoms, distant atoms, and you show that at some point, if you want modules, you would like to entangle different modules, of atoms. Is there a fundamental challenge between this entanglement of entangling a bunch of atoms together? Is there something that you foresee as a difficulty?
Yeah, I may have not played this up as well as I should have, but phases are very important when you have these superpositions. If you're going to entangle two qubits, they come with a phase, and you have to control that. Within a chain, again, these laser beams also have a phase written on them. It's actually not the optical phase, it's a beat note phase. It's a microwave phase that we control, which is a lot easier to do than an optical phase. So the way we do these optical forces, it's only an RF phase we control, and that is written onto the qubit. Now, when we go across distance, it turns out there's not an optical phase written on. So we are able to preserve that phase, and we observe that in our experiments so far. Again, what we're relying on here is that these are atomic clocks. They have a phase that's going at about 12 gigahertz actually, but the accuracy is 10 to the minus 13, so they're very good. So the relative phase between qubits, we have to be very careful on all sources of noise that hit that, but it's not hard to do. I didn't talk about it because I take it for granted. That's not true in superconductors or almost any solid state. They don't have very good atomic clocks, so they have to constantly either feedback and calibrate that phase or do fancy pulse shaping techniques. And as the important thing is, as the system gets bigger, that gets harder and harder and harder to do. It's an impediment to scaling. With atomic systems, we just don't even worry about that. That's almost the easy part. Okay. In the back.
So how can you expect to get good fidelities when relying on single photons, considering that optics always have at least a few % loss, sometimes 10% is pretty normal or larger?
The protocol here is that we're not actually sending information in the photon from one atom to another. What we're doing is entangling two qubits in a given entangled state. They each emit a single photon, and it's a heralded scheme, meaning that, in fact, the probability is much smaller than 1 that it works. It's on the right now. The state of the art is 10 to the minus 4. Okay, that sounds really bad, but we can repeat until it works. So if we do this at a megahertz, 10 to the minus 4, that means we can generate this entanglement at 100 hertz. It's slow. That's the bottleneck. It's slow. But if you have 10 to the minus 4 probability, having a 90%, a 10%, a 1% loss doesn't matter. I mean, just add it to the heap. So it's, thanks for bringing that up. That's the problem with these long distance communication lines. They're slow. Now, they don't have to be as fast as the gates that are in between a single module, but they shouldn't be too much slower. Otherwise, they really bog you down. And so this is going to be the art of designing an algorithm to the system. And we have a given connection graph, and if I have an abstract set of gates, how do I best optimize how it's expressed in terms of the qubits and the connections? And it's always changing. So we need people thinking about that. It's a computer science problem, and a complexity problem, and a compiler problem. But the optical phase never plays a role either because there's 2 photons. Turns out that's very important. So we don't have an optical phase problem.
Thanks.
Yeah, thanks for the question. I should have brought that up. Here.
Yeah. There is a lot of conversation about demonstration of quantum supremacy, and some of the competitors in the superconducting community put the roadmap and very aggressive plans for this. So just curious about your strategy in this domain.
Quantum supremacy. So I showed that plot. Quantum supremacy is something that's going to happen, and it's not necessarily interesting. If it doesn't happen, that's interesting. Sort of implies quantum mechanics is wrong. I mean, so it's not going to be a surprise. It's more of an academic milestone. It's a bright line, put it that way, and it has to do with the performance of current computers more than anything else, where that line is. So, what's our approach to supremacy? I'm not too worried about crossing this line, but what we do want to do is attack a certain type of algorithm, maybe this molecular simulation. That unfortunately scales like maybe the number of qubits cubed, or maybe the 4th power. So it's not exponential, but we'll see how far we can go. And can we, the ozone molecule only has 24 electrons, O3. And the exact ground state was only calculated 10 years ago, I think. So let's go to something more complicated, like benzene, C6H6. That's 42 electrons. That we cannot calculate the ground state. I guess we can measure it using other ways, but doing something like benzene is something that you don't need much more than 100 qubits, and you may need about 10,000 operations, but I think there's promise to even get to that. So I don't worry about quantum supremacy. I worry more about doing a problem that's interesting, going right after that. So look, quantum supremacy will happen. I'll be relieved when we get beyond it. Then it'll start getting fun.
So as you grow the quantum computer to more bits and more error correction, all that, how does it scale? Do you see a fundamental limit in the number of bits that you can realize with that type of computer, just because at some point the error correction is getting so difficult that any large number of qubits just isn't practical, or just won't work?
So yeah, good question about error correction, something I didn't talk much at all about. Now, error correction requires more qubits, so there's an overhead. Just like classical error correction, it requires more bits. And in Shannon's original paper, he showed how you don't need that many more bits to do classical error correction. He even pointed to some codes that weren't so efficient. But quantum bits can degrade in many ways, more ways than classical. A classical bit, it can only flip from 1 to 0, 0 to 1. But quantum bits can lose their phase and so forth. So there are many more ways for errors, so the overhead is much more severe. So indeed, if your error rates are 1%, that's really bad. If you have 1% errors, you probably need a factor of 100,000 overhead. So if you want 10 qubits, but if you want 10 qubits to do a really long computation, and you have 1% error, you need 1,000,000 qubits, because there's an overhead of 100,000, okay? The good news is that as you make the errors lower and lower, the native errors lower and lower, the overhead quickly shrinks. So if your error is at 10 to the minus 5, which is admittedly incredibly hard to do, if your error is at 10 to the minus 5 level, you can get away with maybe an overhead of 20. So things start to look better. So in our platform in atomic physics, we're not thinking about error correction right now. Because passively we think we can get to close, 10 to the minus 5 might be, I would be surprised if there's not a system that can get to the 10 to the minus 4, 10 to the minus 5 level in atomic systems. And then we can think about error correction. So you might say, well, I'm being short-sighted. But there's very likely to be something interesting before we need error correction. Like this benzene molecule. I don't know if you find that interesting, but it's something you couldn't calculate otherwise. And so you might say my head's down, but we're just not worried about error correction yet. But we know that the scale-up is going to be really hard. The challenges in our system are going to be mostly engineering now. We don't need any more physics breakthroughs, put it that way.
So very simple question again. Your system is a 1D. Why not 2D?
I guess I had a comment. It is 1D in space, but the interaction graph of this 80 ion chain is 80 dimensional. So it's not really 1D. So but your question still stands. 2D is interesting because we know, there are a lot of materials in 2D. There's interesting phase transitions that only happen in 2D. 2D is very special. It turns out to be very hard to do two-dimensional systems with ions. With neutral atoms, however, that's much more likely. The problem with neutral atoms is they only have nearest neighbor interactions. So you can't get 80-dimensional connections with neutral atoms. It's very hard to do that. Maybe I'm wrong there, but ions are not well suited for 2D. There are a few exceptions that are, there's something called a penning trap, a different type of ion trap that stores a single pancake in a circular disk. It spins at about 100 kilohertz, so you have to stabilize that, and it comes with some overhead. But the natural geometry for an ion trap is linear. You could make it, it's locally linear, but you can make it turn corners and so forth. But locally it's going to be linear, so 2D is pretty hard.
Hi, Chris. I just want to make a comment that in principle you don't have to have increased depth. You can also have increased number of qubits, and you can still get good fault-tolerant computing. Basically, you have whatever you're going to calculate with ancillars as exactly, of course, entangled ancillars, and then you can reduce the circuit depth. So you will be proceeding along a line that's vertically upwards.
Yeah, but you need to be over here to do that, right? I mean, if you're here, that's not enough. You have to have a critical fidelity to do that. I mean, yeah, I don't know what this blue line does. Well, Hartman drew this. So I have to, the blue line probably has some bending over here. And so what you're saying is you could just go up forever until you hit that. Okay, I believe you.
Yeah, my question has got to do with the engineering aspect of having a box which executes these quantum gates. So I'm assuming you would have some sort of control systems to sequentially read out and perform fast gates. So, and these control systems are, I think, inherently electric circuit based. So are you limited by the speed of the electric current in terms of performing high-speed quantum operations? Or, like, I don't have much of an idea, so this might be a naive question.
So your question concerns the speed of the operations?
Right.
Yeah,
And
okay.
the control system used to, sort of tell say you have a set of qubits and other stuffs like actuators and stuff, which needs to be controlled upon the action of certain qubits. So does this communication happen as fast as you want it to be, or?
No, we always want it to be faster. But I think I did put a couple of numbers here on the physics of these gates, and their speeds are relatively slow, tens of microseconds, and that speed is limited by the fact that the laser apply, it has to push mass, it has to push these atoms around, and that takes time. Now, if you have higher power lasers, you can make that faster, but there are sort of reasonable limits. You don't want megawatts of laser power. So there are issues there. So there's no fundamental limit to this gate speed, but in practice, I think over the next, my guess is over the next decade or two, it's not going to get too much faster than a microsecond. So that could be a problem if you have to do 1 billion operations and each one takes a microsecond. That means it's 10 minutes for the whole algorithm. Well, you have to have a coherence time that's at least 10 minutes. You can do that with atoms. 10 minutes is actually not that bad. Atomic clocks can maintain coherence that long. I don't know if you want to wait 10 minutes for one answer. It sort of depends on how important it is to you. 10 minutes, or do you want to wait 1 billion years on a classical computer? So I guess I didn't mean that to be a joke, but clock speed in quantum computers is not as important as the complexity of the problem that you're solving. If you have an exponential speed up, this will sound overhyped, but if you have an exponential speed up, the clock speed doesn't matter as long as the problem is big enough. But there is an absolute time. We don't want a computation to take a century, for instance. So we always want faster clock speed, but what's more important is just being able to string together a bunch of gates, enough gates to do something interesting. So it's going to depend on the application, and we'll always want more clock speed, that's for sure. But we just have to see how many operations we can string together.
Just a quick thing on that last part. So on this hybrid quantum classical approaches that you do, variational, and you have to do optimization, go back, change the gates, go. Then maybe the speed of adjusting will play a role, probably, but maybe not for small number of qubits, but later on. And depends how fast the whatever algorithms optimizes, but
Yeah,
overall it's
So many of the applications people talk about these days, It's not a single shot where you run a circuit and you get one measurement, you're done. You actually have to do many thousands or even eventually many millions of operations and optimize the parameters in the circuit to get to the right answer. And indeed, the molecular simulation is one of those. And even in the water simulation, to get even close to the true ground state took many days of solid data running. So
that's why you need a good system.
It's tricky, yeah. So clock speed, it's always better to have clock speed, but if you have really fast clock speed and you also have really fast decoherence, that's much worse. One of my colleagues at INQ, he's not a quantum guy. He says, imagine you're at a drag race and you have a dragster that can go 1,000,000 miles an hour and it blows up after 10 feet. But you go 1,000 miles an hour and you can go many miles. What would you rather have? Anyway, that's a little bit goofy, but yeah. Anyway, so if you have fast clock speed, you better have good coherence time. You need to be able to do lots of operations. Fast clock speed by itself is not interesting.
So you've shown the picture several times where you have a long chain of 83 ions or something. What is the maximum distance or maximum number of ions that you have actually measured and verified that the two are entangled? So can you go right up to the ends and say, oh, the one on the 0th ion is entangled directly with the 83rd ion? And if there's some limit, well, I guess, does that come from the uneven spacing or something, or other factors?
Good. Well, let me comment on your second point. The uneven spacing is actually more bookkeeping. It's not, as long as we know what it is, it's okay. We like them to be equally spaced because our laser beams are equally spaced. Optics is a lot easier if you have sort of a ruler and equally spaced them. But the fact that the ones on the end in this trap are not equally spaced doesn't even matter. Secondly, we know how to make them equally spaced. This picture just didn't do that. We have 100 electrodes here. We can control them so they are equally spaced. But your more interesting question was, how many have been entangled, verifiably entangled? And there are many measures of entanglement. Some of them are more subtle than others, but this number is about 20 or so in different labs. Pardon me? 20 qubits. There are some states that where all 20 were entangled, actually. But entangling pairwise, that's a little simpler. I mean, we've certainly done experiments with between 10 and 20. We don't typically worry about distance dependence to that scaling because there's no reason to. I mean, there's no reason that would matter so much. I guess there could be field gradients and so forth, but at INQ we controlled about 15, all pairs of 15. So 15 choose 2. What is that? 70 or something? No, that's more like 100. There are 100 pairs of 15, something like that. 105 pairs of 15, and we can do all of those 105 entanglement operations. So 15 is kind of a small number, but we have full control over that. And the challenge, of course, is to make the system bigger while maintaining full control. I keep saying it over and over again, it's kind of an engineering challenge. Just to do those 105, each of those 105 pairs has a different laser pulse schedule, because we're plucking the string in a different way, and we have to calibrate those, and they drift, and we have to recalibrate them, and things like that. I'm not sure I answered your question that well, but entanglement over many ions has been kind of shown. It's not really in question.
I was just wondering about the number, and you answered that. You said about 20 or so.
Okay. Is that it? Any more questions? All right, if not, thank you again. It's nice to be here.